Assalamualaikum warahmatullahi wabarakatuh to all and to the panel, Dr. Rozina and Sir Muhamad Fauzi. Today I will present my final year project proposal. The title of my project is Lightweight and Portable Chair Fixed Pull Push Dynamometer Testing System. First of all, I would like to introduce myself. My name is Ahmad Shamill and my student ID number is 2018249992. And my supervisor is Dr. Muhammad AZMI bin Abdul. So let us start with the introduction. My project involved in assessing muscle strength, condition, and health. It is important to identify any muscle weakness because it will affect the person's health. The consequences that they may face is exercise intolerance, high hospitalization rate, low quality of life, and even death. Rehabilitation is the action of restoring someone to appropriate training and therapy. The main objective of rehabilitation is to restore muscle strength in the shortest time and to minimize the risk of the re-injury. Pain can be reduced by only rest, but it can expose the patient to the risk of reduced muscle intolerance and increased tissue fragility. There are several methods in assessing muscle strength available. For example, manual muscle testing, handheld dynamometer, and isokinetic dynamometer. All these three techniques have their own advantages and disadvantages in terms of their reliability, responsiveness, size, and cost. This study will focusing on designing and developing a lightweight and portable chair-fixed pull-push dynamometer and to test its measurement properties and to overcome the limitation faced by the manual muscle testing, handheld dynamometer, and the isokinetic dynamometer. Next is the literature review. Firstly, a study has been done on the lower limb muscle strength and recovery. Lacks of lower limb muscle strength have effect of prone to injury, pain, and lack of independence. The consequences they have to face is they are unable to do usual routine, reduce exercise capabilities, and frequent hospital visits. So, it is important to assess the muscle strength precisely and accurately because it is crucial to detect the vulnerability, to assess the impairment, and to optimize the therapy. Next is the study on the methods of measurement for lower limb muscle strength. There are various methods available and it depends on the user for the type of use and the precision level required. Each of the methods have their own characteristics, for example, the data validity, the machine responsiveness, and the reliability. The first method is manual muscle testing or MMT. It is one of the most popular methods used in examining muscle strength. The accuracy depends on the examiner, so they must be knowledgeable in neurology of muscle, anatomy, and physiology. Despite having some drawbacks, it is still beneficial in clinical settings. The second method is by using handheld dynamometer or HHD. HHD have overcome the problem faced by NMT, which is data validity. HHD works by display the value of force exerted by the patient. The limitation of the device is the efficiency depends on the examiner strength, and the device need to be perpendicular to the subject. The device is quite expensive, ranging from 5,000 to 10,000 ringgit. Next is isokinetic dynamometer. Isokinetic dynamometer is the gold standard in assessing muscle strength. This machine have overcome all the issues from manual muscle testing and a handheld dynamometer. The specialty of this method is it can detect a specific joint weakness. Isokinetic dynamometer is the most expensive method, ranging between from 100,000 to 500,000 ringgit, and it requires a large space and a proper setup. For the next section is Finite Element Analysis or FEA. FEA is a physical process model using a numerical mathematical technique referred to as a finite element method or FEM. Static analysis can be used to analyze a 3D model, and the component that can be analyzed is the deflection, the maximum stress, and the factor of safety. There are two research questions for this project, which is, does the newly designed and developed chair pull-push dynamometer are reliable and accurate in calculating and testing the muscle strength. There are three objectives for this project. First is to develop a portable, lightweight and low-cost chair-fixed pull-push dynamometer. Second is to analyze the 3D model of the developed chair-fixed pull-push dynamometer structure. Third is to assess the accuracy and validity of the developed chair-fixed pull-push dynamometer master testing system. For this project, we aim to explore a new design and the new conceptual design of the lightweight portable chair-fixed pull-push dynamometer system. The scope of the project involved on firstly to brainstorm a new concept and mechanism. Second is to develop 3D model using CATIA software. And third is to analyze the static on prototype using CATIA software. The limitation of this project is we only creating a 3D CAD model and static analysis for simulation. Next is the body measurement only considers for Southeast Asian population. Then we proceed with the methodology. This project have been divided into 5 phases. Firstly, the phase 1, which is the initial study. It consists of literature review, identifying the current problem and the data collection. Then the phase 2 is the concept generation. We have done the sketches of civil design, mechanical mechanism, and the initial dimension. Then we proceed with the phase 3, the computational design. The sketches have been transferred into 3D model using CATIA software and 3D rendering prototype presentation. Then we proceed with the phase 4, which is the integration of IoT. The master testing system have been developed to work with the Wi-Fi development board and the sensors. Then, lastly, the phase 5, which is the analysis and evaluation. After all the previous phases have been done, we can proceed to validate the newly developed chair robustness and the accuracy on measuring the muscle strength. Next, we proceed with the expected result of the project. We are expected to fulfill all the stated objective given. So, we have to provide the 3D model of the new prototype with detailed drawing and the data from the simulation. And the finished product are expected to be beneficial to the health examiner by reduce the cost while having the reasonable accuracy, reliability, and the responsiveness. This is the preliminary result of the project. The master testing system have been developed, and this is the block diagram shown on the figure 7. It comprises 3 subsystems and 2 interfaces, which is the machine operator interface and the patient machine interface. The control subsystem is where the operator receives the data from the measuring system, and the measuring subsystem consists of force sensor to measure the force transmitted and the potentiometer that indicate the lower limb angle. And lastly, the mechanical subsystem, which is the chair for evaluating the patient. This is the circuit diagram for the force sensor. In the circuit, figure 8, it consists of force sensor, ESP32 microcontroller, a capacitor, and a resistor. With the Wi-Fi development board ESP32, the data can be uploaded into the IoT platform such as web server for Blink application. For the project, we need a force sensor that capable up to 30 kg force. The value of the force can be increased by reducing the resistance value. Also, the force sensor need to be calibrated so the data display is accurate. Lastly, this is the 3D prototype that have been created using CATIA CAD software. The seats are used from new product or recycled product. Only the bottom part needs to be designed, so the seat is negligible when the static analysis is done. Figure 10 shows the product that have been designed and assembled. To design this product, this is the feature needs to be included. Firstly, the leg of the master testing can be adjustable to 90, 60, and 30 degree. The product also need to be heavy duty so it can withstand heavy weight and portable. The footrest and the force sensor are rotatable, so the patient with left or right dominant leg can use this product. This is the reference used for this presentation slide. And that is the last slide of my presentation. Thank you for your time and attention. To ask me any question regarding the project, feel free to contact me by the email or leave a comment below. Thank you.